In this video, we're going to talk about the concept of force and net force. In my earlier videos, I discussed how to describe a motion with pictures, graphs, and equations. But until now, we have said nothing to explain the motion. Now we turn our attention to the cause of the motion, forces. This topic is called dynamics, which joins with kinematics to form mechanics, the general science of motion. Let's first take a closer look at the meaning of force. It is easy to give examples of forces, but how would you generally define that concept? An operational definition of force is based on observed effects. That is, a force is recognized and described in terms of what it does. From our own experience, we know that forces can produce changes in motion. A force can set a stationary object into motion. It can also speed up or slow down a moving object or change the direction of its motion. In other words, a force can produce a change in velocity. That is an acceleration. Therefore, an observed change in motion, including motion starting from rest, is evidence of a force. This concept leads to a common definition of force. A force is something that is capable of changing an object's state of motion, that is changing its velocity or producing an acceleration. The word capable is very significant here. It takes into account the fact that a force may be acting on an object, but its capability to produce a change in motion may be balanced or cancelled by one or more other forces. The net effect is then zero. Thus, a force may not necessarily produce a change in motion. However, it follows that if a force acts alone, the object on which it acts will have a change in velocity or an acceleration. The concept of force gives us a quantitative description of the interaction between two objects or between an object and its environment. When you push on a car that is stuck in a snow, you exert a force on it. A steel cable exerts a force on the beam it is lifting at a construction site, and so on. Each of these examples show that the force, which is a push or a pull acting on an object, has both direction and magnitude. When a man is pushing on an object, it is exerting a force on that object in one direction. So usually we denote the force with the capital letter F, and it's very important that you use capital letter F because lowercase f is occupied for something special. And it's a vector because it has a direction as well. In the second picture, we have a pull when a person is pulling an object. So the force is actually this direction to the right. And then there is the object that is hanging from a rope, for example, or a string. In this case, the force is again being pulled by this rope. The rope is pulling, or the string is pulling the object, and the person is pulling on the string. So there is another situation where you have, let's say, a ball falling down. Okay, so in this case, nobody is pushing it, but is there anything that is pulling it? Well, obviously, it is, we know it is accelerating, and we know that it's a free fall. Acceleration is gravitational, so therefore there is a force that might be pushing, pulling or pushing. Let's try to understand what might be that pushes or pulls the ball to fall down. Apparently, that's the earth that is pulling it. Earth is the agent. So it is very important to understand whenever you have a force, you need to have, for force to happen, you need to have an object and agent. Maybe it's better to write that the agent applies a force on object. In the first situation, you can see that the agent is the person who is pushing, the object is the whatever crate it is. And in a second situation, we have the person to be the agent and the crate to be an object. In a third situation, the rope is in contact with the object, so the rope is the agent, and the whatever object is being pulled up, it's the object. So with the in the fourth situation, the earth is the agent and the ball is the object. In the future, when you solve problems, try to identify what is the object and what is the agent. That might help you identifying the forces in the future. As I talked already, I said force is a vector quantity. It has magnitude and direction. And force is actually measured in newtons, in honor of a scientist of Newton. N is a must be uppercase. There are two types of forces: contact forces and long-range forces. These two basic classes of forces, depending on whether the agent touches the object or not. So the contact forces are forces that act on an object by touching it at a point of contact. Long-range forces are forces that act on an object without a physical contact. For example, a bat must touch the ball to hit it, like in a baseball bat. A string must be tied to an object to pull it. The majority of forces that we will examine are contact forces. With the long-range forces, we will identify the magnetic force, electric force, gravitational force. You have undoubtedly held a magnet over a paper clip and seen that the paper clip leaps up to the magnet. A coffee cup released from your hand is pulled to the earth by the long-range force of gravity. Another important thing about the forces is how we represent the force. You have noticed already that when I used my diagrams here, I used an arrow to represent the force. But in reality, if you want to simplify a case, simple diagram to visualize how forces are exerted on an object. Because we're using the particle model for an object, in which objects are treated as points, the process of drawing a force vector is very, very straightforward. So you can take a small dot that represents the object as a particle. So this one is your object as a particle. And then you will place the tail of the force vector on the particle. So here's the tail of the force vector on the particle, and here's the head of your force vector. When you draw a force vector as an arrow pointing in a direction that the force acts, and what is the length that will be proportional to the size of the force, and then give the vector an appropriate label. Let's say you put a force, it could be force 1, force 2, whatever subscript it has, and then you put the arrow, little arrow on the top. In this situation that I drew, the box which represents the box is your object. So therefore, if you want to draw a box in a particle representation, you will do a small dot, okay? And then agent is your rope. So, and if you want to understand who is pulling the box is in immediate contact with the rope, so the rope is pulling. That's why rope is the agent. So the force, the pulling force, will be starting from the point, the tail of the vector. So you would represent pulling force in the form of vector, and because it's a special force that is associated with the ropes or the strings, we have we call it a tension. So pulling force of rope, and it's a special one, so we denote it with the capital letter T as a tension. We'll talk more about this. So in this next situation, we have the spring that has been initially compressed, and a box is attached to the spring, and then you let it go. The spring is going to act on the box by pushing it forward. So the spring is actually the agent here, because that is in an immediate contact with the box. So let's call it agent. And the box is our object. If we want to draw a picture, the diagram picture, the point for as a particle, so we will make the object to be the dot, and then agent, that is the spring, is pushing. So that means my vector, although in the picture you see that this is pushing this direction, the spring is pushing forward, but we always put the tail of our vector at the particle. So here is how you represent the force of the spring. And we will put a subscript here to identify it's a spring force. So let me write this here: pushing force of spring. It's important to understand. You can actually personalize it. You can think of sorry for the comparison, but you can think of that you are the box and you feel that force. Therefore, the force has to be originated from the object. Another situation is when you can have a box falling to the ground. So let's say this is the ground and we have a box that is falling. So in this case, we have the earth and the gravity is pulling the box. So your agent here is the earth. So earth is the agent, and the object is still your box. Remember what we do? We take the object and make a particle, okay? And the object feels the force of the earth. So force is pulling it downwards. So we go and put this vector going downwards, the tail always on the object. Okay, so we can write this as a force of gravity. This this force, the pull of earth, has another name that we will talk about, and it's known as a weight. In different texts, or different people have a different preference of drawing these simplified particle diagrams. For example, if you want to draw a force, pulling force, tension force on an object, let's say you have a box and you're trying to pull this box with the rope. So this rope is pulling. So people may do this. They put their object as a particle right in the center of the box, and then they draw a force starting from this object going to the direction of, so it's called tension force right here. So that's another way of doing. Or falling object could be drawn this way. So this is your falling object. You have a dot. Sometimes it's convenient, sometimes it's not. And it depends on which book are you looking at. So here it would be force of gravity going downwards this way. And maybe you would be interested also for the spring force. Let's say we have a box that is sitting on the floor and the spring is pushing it, right? Okay, and you put the particle at the center of the object, and then the force from that point. Okay, so this would be force of spring. This is another way of doing it. Now let's think what will happen if you have more than one force acting on an object. For example, you could have a box. Let's just keep consistent with our colors. So let's say we have a box, and a box is being pulled into two different directions. So if you look at let's say a top view of this box is being pulled by one person in one direction, let's say here by one rope, and another one is pulling downwards. So there are two forces apparently. Now we can do represent the box, the pull is this direction, and then the other pull is this direction. Now you can represent the box as a dot, okay? And then one force could be going, let's say, this direction with the force 1. And then there is another force going downwards. Let's say a little bit shorter force. Okay, now how would we find what is the combined force? The experiments showed that when several forces are exerted on an object, they combine to form a net force. Okay, so what is a net force? Net force is the combination of all forces together. So we define as a F net equals, and it's a vector, force 1 plus force 2 plus force 3 plus as many forces as you have. This is known as a superposition of forces, mathematically known as superposition. Superposition of some quantity is very much used in physics. So we will come to this concept again. Superposition of forces. Now going back to our example, we have two forces right here. We could write, actually, let me keep that space free because I want to graphically represent how the forces, what is the sum of the forces. I can use the parallelogram method and find the net force or resultant force to be here, F net. Pretty much is the resultant force. You could also do the head to tail method. If you bring the F to, let's say, bring the F to in here, you will see F net is the same. Anyways, this F net force is the sum of force F1 plus F2. Remember, this is a vector addition, so you might need to later on to use component methods of adding vectors. Thanks for watching. Stay tuned for more.